Okay, let's continue with the next example, and clearly this is an alternating series, and AK is ln k over k. So test 1 is simply to check what is the limit of this sequence AK, of these terms AK. So we have seen this before. Clearly this is infinity over infinity form. So we are going to go to ln x over x and see what happens as x goes to infinity. So using the L'Hopital's rule, you'll take the derivative of ln of x, which is 1 over x, divided by derivative of x, which is 1, which is 1 over x, and this goes to 0. So therefore the limit of this is 0, which satisfies the first test. Now let's try test 2. So here we have to show or check that AK plus 1 is less than equal to AK. And this time we are obviously not going to try doing it algebraically, especially with log involved. So we are going to use the function form of it. So f of x would be ln x over x. So now let's use the quotient rule to find the derivative of this function. So the quotient rule will give us the derivative of ln x is 1 over x times the denominator, which is x, minus the numerator, which is ln x, times the derivative of the denominator, which is 1, divided by square of the denominator. So this is very simply 1 minus ln x over x squared. But remember, this is always positive. So the question is, what about the numerator? Now we know that ln x is an increasing function. Therefore, 1 minus ln x is definitely going to be less than equal to 0 after some x, let's say greater than 4 for sure, because the graph of ln x looks like this. So this is going to be more than 1 definitely after x equals 4. So test 2, yes. So since both tests are satisfied, we can say that the given alternating series converges. Okay, finally you can practice with this particular one. So AK, let me start you off. AK would be 1 over k ln k. Test 1 is trivial because limit k going to infinity 1 over k ln k. Now this is going to infinity, this is also going to infinity, so we have no problem. This definitely is 0. So first test is simple. Now you'll have to do the second test. So Again, in this particular case, you would use the derivative. So f of x is 1 over x ln x. So you can find the derivative f prime of x. So let me just write what it would be. It would be negative ln x plus 1 over something squared, actually simply x ln x squared, but we really don't care for the denominator, and this term is less than equal to 0, obviously, because you have the negative sign in front of positive numbers. So this is after x more than 1, this ln x plus 1 is positive, so you have a negative sign in front of it. So test 2 is satisfied. Therefore, again, the alternating series converges. Now, if either one of these two tests had failed, then we would say the alternating series diverges. You'll see later on when that happens. Okay, so the final section in this alternating series topic is the concept of absolute and conditional convergence. Again, first I'll try to explain intuitively and give you the idea, and then we'll do the mathematical and a mechanical version of it. So some students find this concept a little confusing, but hopefully it will be clear with these examples before we give the formal definition. So please try to understand this. So first thing is, in this section, when we write a series in this manner, we mean that this is the complete series. So what I mean is, suppose you have this series. Now, in this particular section, from now onwards, when you see this as the series, AK is the complete term, is the full term that we are talking about. In the alternating series test, remember, or just a few minutes back you must have seen that AK was the non-negative alternating portion. So AK, we were just picking out the functional part of it, but here AK is the complete thing. So this whole thing is AK. Please remember this subtle point. So in other words, AK includes the negative 1 portion. Okay, so let's again recall some of the stuff that we know very well. So here are some cases. So case 1. So look at this series. This is the 2 series. We know very well that this converges, right? Okay, then we look at the alternating version of it. So this alternates, this we know it converges. We can check it from the alternating series test, but actually this convergence is for free if we know that this one converges, because this is the absolute version of this. So let's see what I just said. So here the series AK is the alternate series, which is in this B here. So please pay attention to the notation. So when you have summation AK, the absolute value, when you take the absolute value of AK, that gives you the absolute series. So this was AK, and when you take the absolute value of it, you get the absolute series. So that's what is being told here. So now the absolute series converges, then we say that the given series, the alternating series, converges absolutely. So let me rephrase it. If the absolute version of your alternating series converges, then we say that the alternating series, the one that we are given, converges absolutely. Okay, case 2. Now suppose we have the harmonic series. Now here, this series diverges, and when it's alternating, it converges. So what does this example tell us? Okay, so AK is the alternating series, which is this guy, this one. You take the absolute value, and that is called the absolute series, which is here. Now here the absolute series diverges. We know that the absolute series diverges, but the alternating series, the one that was given to us, converges. It converges. So in this case, we say that the alternating series converges conditionally. Okay, so let me rephrase it. So you have an alternating series AK that converges, but the absolute version of it diverges. So when that happens, we say that the alternating series, this one, converges conditionally. So this leads to the following definition. So this is how what I've explained written formally, so you can read that slowly and understand. So again, trying to rephrase it. So let's write it in some simple terms. Remember that all this is about alternating series, and it's written as this. If the absolute series converges, then the alternating series converges, and that is for free. And we say that the alternating series converges absolutely. Next, if the absolute series diverges, then the alternating series may converge, as we know for harmonic series. Then in that case, we say that the alternating series converges conditionally. Of course, it's possible that the alternating series may diverge, and then obviously we just say that the alternating series diverges, so there is no problem with that. Okay, so here is the theorem that we have been mentioning to you, that absolute convergence implies convergence. So what that means is that if the absolute series converges, then the alternating series converges. It makes intuitively perfect sense. Okay, so how do we figure this out? So given an alternating series, how do we figure out whether it converges absolutely or conditionally? So the process is as follows. So this is a pictorial way of explaining this, and this is a step-by-step algorithmic way of explaining this. So let me explain this pictorial way. So we are given the infinite series, and this is the alternating series. Okay, so you apply the alternating series test. You figure out whether it's divergent or convergent. Now obviously if it is divergent, then you say divergent and you are done. There's nothing more to do. Now if it converges, so if the alternating series converges, then you take the absolute series. That means you drop the negative sign, take the absolute series and test. Now these are the old tests of previous section, and find out whether this series, absolute series, converges. Now if it converges, we say that the alternating series absolutely converges. On the other hand, if it diverges, it means the absolute series. Then we say that the alternating series conditionally converges. Okay, some students find it more convenient to understand in this manner. So, step 1. Use alternating series test on the given alternating series. If it is convergent, go to step 2. If it is divergent, stop and just say that the given series diverges. Okay, now we are on step 2 if we came through this part of the stepping. So you take the absolute series, you apply the earlier convergence tests. If convergent, so that means if the absolute series is convergent, then the given alternating series is absolutely convergent. If the absolute series is divergent, then we say that the alternating series is conditionally convergent. Now think about this carefully. First time round it may seem confusing, but actually if you read it few times you will see that it makes good sense.